You clicked this video because you heard binary search trees are obsolete in modern engineering. You likely think they belong only in computer science textbooks while your codebase relies on hash maps and vector databases for everything real-time. The reality is that these structures have quietly become the secret weapon powering low-latency inference in production. AI systems, specifically within GPU, accelerated retrieval pipelines where milliseconds matter more than ever before. By watching this explanation, you will discover exactly when and why a binary search tree outperforms complex hashing schemes to deliver sub-millisecond latency for approximate nearest neighbor search that other structures simply cannot match. For years, the narrative has been clear: learning binary trees is an academic exercise with little practical value compared to modern alternatives like locality sensitive hashing or flat vector stores. This perspective creates a dangerous gap in your engineering toolkit because it ignores how specific data topologies behave under extreme load. The problem arises when you assume that all high-dimensional search problems require the same solution, leading many teams to deploy generic indexes that struggle with memory bandwidth bottlenecks during peak concurrency. You might have felt this frustration firsthand when your system slows down, precisely when traffic spikes and users demand instant answers from millions of data points. Here is what most tutorials do not tell you about binary search trees in the context of artificial intelligence. They are not just generic containers for ordered data anymore. In specific scenarios involving binary vector spaces, they have evolved into specialized inference accelerators that preserve structural distance metrics, which hashing algorithms often collapse or destroy entirely. When a system needs to perform approximate nearest neighbor search on millions of descriptors without sacrificing precision, the traditional approach using locality sensitive hashing can fall short by over 20% in accuracy while maintaining similar memory footprints and recall rates. This is not a minor statistical fluctuation. It represents a fundamental difference in how these structures handle geometric relationships within binary data spaces. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Consider the architecture of a modern retrieval augmented generation pipeline where image localization or feature matching must happen in real time. If you rely solely on hashing techniques, you are essentially trading off structural information for speed, because hash functions group items based on similarity rather than preserving their relative positions in space. A binary search tree maintains that spatial hierarchy through its branching logic. This allows the system to traverse fewer nodes to find a match, resulting in deterministic retrieval times with logarithmic complexity even as your dataset grows into the millions. The result is sub-millisecond latency that becomes critical for user experience when every millisecond counts towards perceived performance. The confusion often stems from mixing up different types of tree structures used in computer vision and machine learning. You might have encountered references to binary partition trees, which are designed specifically for image feature attributions rather than indexing operations. These two concepts serve fundamentally different purposes within the same broader field of visual computing. A binary search tree is optimized for finding items based on key values or vector proximity, while a binary partition tree focuses on assigning importance scores to specific regions of an input image. Conflating these structures leads engineers down the wrong path when trying to solve indexing problems, wasting time implementing solutions that do not address the core latency issues in their retrieval systems. In high-stakes environments like real-time computer vision or large-scale database management, standard implementations often suffer from poor cache utilization compared to more modern alternatives. Traditional B+ trees can become bottlenecks because they require locking mechanisms during updates, which creates contention when multiple threads try to access the data simultaneously. This is where specialized variants step in to solve the concurrency problem without sacrificing speed. Engineers have developed latch-free feature B+ tree architectures that achieve between 2 and 3.7 times faster update speeds under high concurrent loads compared to their standard counterparts. These optimizations prove that with the right design patterns, binary search structures can compete directly with trie-based indexes even in main memory environments where cache locality is everything. The shift from viewing these trees as static data containers to dynamic inference components changes how you approach system design entirely. Instead of wrestling with complex vector quantization methods that introduce additional computational overhead and potential accuracy loss, you leverage the deterministic nature of binary search within specialized GPU-accelerated pipelines. This trade-off favors algorithmic simplicity for guaranteed performance under load. You are essentially bypassing the intermediate steps required by other indexing strategies to achieve a direct path from query result to final output. The mathematical guarantee remains constant regardless of data size because every operation scales logarithmically, providing predictable behavior that is essential when your system must handle unpredictable traffic spikes without degrading service quality. This utility is not universal, though. A binary search tree does not inherently solve latency issues for general high-dimensional real-valued vectors unless the data has been transformed into a binary representation or possesses specific topological properties. In contexts where vectors are continuous and lack clear binary boundaries, other methods like approximate nearest neighbor search algorithms based on graph structures might still be necessary. The key insight is that you must analyze your data topology before choosing an index type. Understanding whether your vectors exist in a binary space or require complex real-valued approximations determines which structure will actually accelerate your inference pipeline rather than slow it down through unnecessary complexity. When you recognize this distinction, the role of binary search trees becomes clear as a targeted optimization tool rather than a general-purpose solution for every search problem. They excel where exact searches are computationally prohibitive and where preserving structural distance is more valuable than raw throughput alone. This realization allows junior engineers to move beyond textbook definitions and apply these structures strategically in production environments where performance margins are razor-thin. The technology has moved past the academic phase into a practical necessity for building robust, low-latency AI systems that can handle the demands of modern applications without compromising on accuracy or response time. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.